So in this section, we're going to talk about how much radiation is emitted from a surface, different from the reflected radiation that we had talked about in the past. So before that, I have a question for you. So this is a picture of my class. An infrared camera took this class picture without any sunlight and with fluorescent lights on. So the question to you is, can you guess what the picture will look like when the fluorescent lights are turned off? Do you think it'll just go completely dark? If you recall from your night setting of your video camera, you can take pictures in the dark. So here it will not go dark. In fact, if you believe me, the picture will pretty much stay the same. I'm not showing you because I don't recall taking the picture with the lights off, but I recall seeing it in class. So it's going to stay the same. Why is it so? A simple explanation is we normally see things using the light reflected from a surface. But this camera is using thermal radiation emitted from a surface. So it's seeing emitted light. And the emitted light does not change, stays the same. Emitted light does not change, so the picture will pretty much stay the same. Now, emission from an ideal body can be theoretically calculated. That's what we're after. So what's an ideal body? Ideal body is defined one whose absorptivity is equal to 1. Such a body would have no reflection, and it also does not transmit anything. So it neither reflects nor transmits, thus it absorbs all radiation, and hence it's termed black. So why black? In the visible light, if a body reflects no radiation, we would see it as black because there's no light coming off of it. We just wouldn't see it. An extension of this fact is being used here to refer to zero reflection, not just in the visible light that we normally know, but over all wavelengths. So such a body it absorbs everything and reflects nothing over all wavelength. And it's called an ideal body or a black body. So how much does an ideal body emit? This can be theoretically calculated. So purely from theory, we can find the emitted energy flux per unit wavelength. So it is flux, energy per unit area per unit wavelength is given by this. So this, you can see the units, it's watts per meter square per unit wavelength. And notice that this amount that is emitted is a function of temperature. So this is absolute temperature, of course. Absolute temperature, and it also is different at different wavelength. You can see lambda here and lambda here, so it's a complex expression, but it's going to give us the amount emitted at a temperature at any wavelength. Now this equation for the amount emitted will be plotted. So the expression for the amount of energy radiated uh, per unit wavelength for a temperature, so the energy flux that we got in the previous slide is plotted here. And notice that these other quantities like the speed of light, c and h is Planck's constant, kappa is some other constant called the Boltzmann's constant. These are known values, okay? And so for a given temperature, I can plot EV lambda versus lambda. That's exactly what is done. So it's plotting versus lambda here. And we chose three temperatures, 5800, 1000, and 300. Now, why did we choose 5800, for example? It so happens that 5800 is approximately the sun's surface temperature. And 300 is somewhere near what our body surface temperature would be. It's near, not exactly. One important point to note is the solar radiation actually follows this curve very close. So it is closer to an ideal, whereas our body surface really does not follow this. This is the radiation emitted by a surface that is close to our body surface temperature, but it's an ideal body. Our body is not ideal. More will be discussed later. Okay. So what observations can we make of these three curves? So three important observations. First one, that the energy emitted, the energy flux. Remember the unit for this is watts per meter square per micrometer. The watts emitted varies continuously with lambda, meaning there's some amount emitted at all wavelengths. Okay, that's one. The second one is the amount emitted, that's this, the amount, the magnitude emitted increases with temperature. And notice the logarithmic scale here. That means the amount emitted at the sun's surface versus amount emitted by let's say our surface, there will be at least a 6 orders of, or it's at least 1,000,000 times more of what we would expect at sun's surface. The other observation is that most of the energy emitted is near lambda max. Lambda max is where this one is. Most of the energy emitted is near that. This is also may not be apparent from the log scale here, but notice that by the time you come from here to here, there is a 2 order of magnitude difference, which means by the time you go to this wavelength, it's only 1% of what is at lambda. So then most of the emission is near this lambda max. Okay, but how do I find where this lambda max is? Now notice this is a function of lambda. So I need to find where the value of the function is maximum for what lambda. So that, of course, the process would be to take dV lambda and differentiate with respect to lambda, setting it equal to 0. That will give me the value for lambda max. And if you do that numerically, this is the formula that you'll get. Lambda max times T is equal to 28.97, meaning it's a constant. This is very important relationship. So higher the temperature, lower the wavelength around which the maximum amount is emitted. Higher the temperature, shorter is the wavelength. We want to calculate the fraction of energy emitted between two wavelengths. So that will be energy emitted between two wavelengths, EB lambda integrated between lambda 1 and lambda 2 divided by EB lambda integrated over all wavelengths. And over all wavelength, we know it's sigma t to the 4. And so we can substitute that. Now, this integral here between lambda 1 and lambda 2, we can break the integral. And the first term, 0 to lambda 2 EB lambda d lambda, will be energy emitted up to the wavelength lambda 2. So if this is my lambda 2, then the first integral is all of this area, right? And then the second integral, this one, suppose I have another wavelength lambda 1, then that would be all of the area under this. Now both of them still divided by sigma t to the 4. So we take this total area minus we subtract this area. That gives me the energy in this region. Okay, because we are doing this at one temperature, we can change the variable of integration this way, or we can bring first we bring sigma t to the 4 inside the integral because t is a constant. So we can write it this way, and then we can change the variable of integration this way, where we divide and multiply by t, so it stays the same. So basically the difference between these two integrals is this area. That's the energy between these two wavelengths, but it is not just the energy, it's the energy divided by the total amount of energy, because remember we already divided by sigma t to the 4. Notice that EB lambda over sigma t to the 5, if I plug in for EB lambda the expression that we had and rearrange, we see the expression is a function of lambda t together, meaning it's not separately a function of t, which means if I need this integral, it's kind of we can get it from one universal function, because this part is only a function of lambda t. So we don't have to do separate integrations for every different temperature. We can have one universal function that if we integrate with respect to lambda t, we can get this first of the two integrals that we had from previous slide. So this we call as function f. So the function f, the meaning of it is the amount of energy from 0 to any wavelength lambda 2 multiplied by the temperature we're talking about. And so this is the amount of energy, but it's not the absolute amount. It is a fraction of the total energy. So what this means is if I have lambda 2 here, then that integral gives all of this area divided by the total area under the curve. So it's the fraction of energy up to that is there up to the wavelength lambda 2. And likewise, this one is for lambda 1. And so this f fraction or the f curve is basically this integral, but it is tabulated. It is tabulated in any text, and our text also has it. So we can just read from the tabulation what is this f value. We're going to see this in an example right away. So here we want to apply the formula that we derived. Okay, so our question is, what fraction of solar radiation is useful for photosynthesis? In particular, what fraction of the solar radiation is within this wavelength range? This is not millimeter, this is micrometer. Within this micrometer range, the sun's surface temperature is provided to be 5800 degrees Kelvin. So this is a direct application of what we just did. So this curve here is the radiation emitted over all different wavelength. And on this curve, what we're trying to calculate is what fraction of energy is between 0.35, so 0.2, 0.3, 0.35, this line here, and 1, 2, and 0.7, 4, 5, 6, 7. So it's somewhere here, 8, 9, 10. Yeah. So what we are trying to do is not just this area, but how much energy is there in this area as a fraction of the total area. So the total area from 0 to infinity, if we just find the total area under the curve, how much energy is here as a fraction of that total. So this would be given by, this can be calculated very directly using the f value. So what we need is the f value between 0 and this lambda t. So t times lambda 2. So what this f value means is what is the area under the curve between 0, 0 all the way to 0.7. The area under the curve, the area under this curve divided by the total. That is the meaning of this f value. And likewise, this other f value between 0 and t times lambda 1 is the area under the curve. Sorry for the mess here. So area under the curve here divided by the total area from 0 to infinity again. Okay, and so basically then we need to look up the f values between 0 and 4060, which is 5800 times 0.7, and 0 and 2030, which is 5800 times 0.35. So if we look up the tables, then this value is 0.49, and then this value is about 0.07. So the difference is about 0.42. And what is the meaning of this 0.42? This means the area under the curve between these two wavelengths is 0.42 or 42% of the total area under the curve for 5800 degrees Kelvin. So this as a fraction of total area. So then this is a nice way to find out, let's say, between then 0.35 and 0.7 micron, how much energy or what fraction of the solar energy is there and is therefore useful for photosynthesis.